Good evening, everyone, and welcome back to our last day for security analysis, domain analytics. So far, we have understood what we mean by security in terms of finance. We are taking a look purely on a financial basis. So we have the finances of different companies, different types of financial securities like stocks, bonds, mortgages, uh, what do you call it? And even cryptocurrency, which is again a bit of a debate whether it should be considered as financial security or not. We have also understood how money laundering works and how money laundering is used and how we can classify different types of money laundering. All right. So that is something that we have understood. Then we went through the process of CRISPR-MLQ. What is CRISPR-MLQ? What are the different stages of CRISPR-MLQ? What all is covered in these different stages? We looked at it. Then we started looking at unsupervised machine learning. In unsupervised machine learning, our output is not known. Our Y is unknown. So we don't know what our output is. We just have some data. So we try to find out some patterns or rules within that data. So for that, we understood k-means clustering. So here we are trying to cluster different types of data. All right. So afterwards, we started taking a look at supervised machine learning. In supervised machine learning, our output is known. We know what sort of output we have and what data type output is. It can be continuous or it can be discrete. And we can work with either of these problems. All right. So in this, we started off with k nearest neighbor, trying to classify different data points based on its nearest neighbors, based on which data points are nearest to it. Then we went ahead and we looked at decision tree. In decision tree, we were dealing with categorical data and we were trying to make complex decisions. All right. And then we looked at linear regression. In linear regression, we are taking some data points and we are trying to fit it on a line. All right. And today, finally, we'll take a look at neural networks and how neural networks are useful in financial securities. All right. So that is the purpose of our session today. So let's get started. So we'll be understanding neural networks. All right. We'll understand what is multi-layer perceptron algorithm. We'll understand activation function, error surface, and gradient descent algorithm. So we'll go through all of these points today. So the human body is controlled by our brain. All right. And our brain is nothing but a network of neurons. These neurons are the decision-making hub of our body. All right. All the decisions that we make are made within these neurons. All right. So whenever we are trying to think something, for example, right now, I'm speaking. In the back of my mind, I am thinking about what I will speak. Then that information is processed within these neurons. It's like an input. All right. That input is processed within these neurons. That information is sent into my mouth. My mouth will make the movements that will lead to changes in the air pressure that act as sound coming out of your mouth. Similarly, when you're walking down the street, right, and you see something and you look at it and you process what you're seeing, it is happening based off of neurons. These neurons extend all over our body, from our brain to the ends of our body. That means your fingertips, your toe tips, all parts of body have neurons. That's why anytime you feel any sort of pain anywhere on your body, it is those neurons reacting. It is those neurons reacting and processing this information. And the signals are sent in form of electric signals. And they are extremely fast. The more neurons you have, the faster your neurons will work, because it becomes easier for the work to be divided. All right. So this is what our neuron looks like. So you have these dendrites. These are the edges. These dendrites are connected to a cell. And these cells have a nucleus within it. Then you have these axons and the axon terminal. So what happens? Some input is given to the human body. That input in the form of electric signals is passed through various neurons. All right. And then we process it. We send it to our cell. Our cell will take that processing and take care of the final output that happens at these axon terminals. All right. So this is the basic process of how a human brain works. All right. So then we try to mimic it. We mimic it using artificial neurons. All right. We mimic it using artificial neurons. These neurons are called artificial neuron because we are basically replicating the same structure as a brain, but in a virtual setting, hence the name artificial. So it will not have the same, the structure is the same, but because there is no organic body containing these neurons, we call it as artificial neuron networks. So we have these input layers. These input layers will receive some input, like the name suggests. Within these hidden layers, these two hidden layers, we have the processing happening. And once the processing is happening, we are getting some output. All right. So the same step as the human brain. You are getting some input, the layers, the dendrites are working on it, and then you're getting the final output at the axon terminal. So the same thing is happening here. All right. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9. You have 9 neurons here that are working in processing of these decisions. So each of these inputs, input 1, input 2, input 3, it will be sent to all these neurons, each and every one of them. Each and every one of them will receive some sort of neuron. All right. And these neurons will process the information and then will send that information to the next layer of neurons. And the next layer of neuron, based on the previous processing and its own processing, will give us some output. So you have 2 hidden layers that are doing all the work for us. All right. So moving forward. So again, neural networks are inspired by biological neurons. All right. So These biological neurons refer to a brain. So human brain has around 85 billion neurons. We have 85 billion neurons. And these 85 billion neurons are responsible for everything we do, every single decision we make in our life, every single action we take at any time. These 85 billion neurons are responsible for that. Cat has roughly 1 billion neurons. You can already see the difference is 84 billion. The difference is 84 billion. So the amount of information a cat can process is far less than what a human can process. A mouse is even less. A mouse is 75 million. The difference is what? 84.925 billion. Again, a mouse is a lot less smarter than a cat. And a cat is a lot less smarter than a human. And finally, a cockroach only has 1 million neurons. Now here you can understand that cockroaches are nothing but an annoyance. They are just creatures who don't have a lot of ability to process information, who are there to either scare people or to annoy people. But artificial neural networks only have several hundred. All right. So you're looking at hundreds of neurons. So in a way, these artificial neuron networks can process way less information than a cockroach can, a mouse can, a cat can, let alone a human. So all this talk about, what do you call it? All these talk about AI taking over the world, it's nothing. I always say that a dog is smarter than what your machine can do. But these several hundred neurons are enough to process complex information. All right. So you can process any sort of complex information. But the thing is, these neurons, they are trained only to do one thing. Most of the time, anytime you build an artificial neural network, it is you're building up some pattern recognition, you're building up some memory for these machines. All right. So these neural networks, they're designed for usually just one purpose. If you have a neural network that is designed for facial recognition, all right, then this one cannot work for a chatbot. It cannot work for a generative chatbot. All right, these generative chatbots are chatbots that don't store information, that you don't have to tell them that this is the question, this is the answer. Obviously, initially you do that, but over time, it remembers all these things. It is able to understand questions, different questions that are not within its database, and it is able to find the relevant answers. But like I said, if you have a facial recognition system, it cannot be used in a generative chatbot or any chatbot for general, any chatbot in any scenario. You have to train a different neural network. So you're building a collection of neural network. Anytime a company is talking about, our neural networks are doing this, our neural networks are doing that, they're talking about a collection of neural networks, a different set of neural network. It's not just one neural network that is doing all these tasks. Okay. So this is this is how neural networks work. Now, neural networks are part of deep learning. Okay, so far we have taken a look at machine learning. Now, deep learning and machine learning are both subset of data science and AI. All right, AI is the master of it all. Then you have data science, machine learning, and deep learning. Okay. So deep neural networks, they are part of deep learning. Okay. So these neural networks that are working towards interactive AI based systems. So these in deep learning, if you go in depth, you can apply supervised, semi-supervised, and unsupervised learning. Okay, so you can apply any of these. All right. So it is called deep neural network because it is dealing with far more complex problems. And as the complexity increases, the learning curve becomes more complex. So you have to go more and more into the depth of that curve, and you have to dig out some solutions. So this is why it is known as deep neural networks. Now, deep neural networks can be of three types. You have artificial neural networks or multi-layer perceptrons. So this is what we'll cover today. Then you have convolutional neural network. These neural networks you'll often see in image processing related problems. Anywhere you see a person using image recognition related problem, you'll see that they are they are always using these convolutional neural networks. And finally, you have recurring neural networks. These recurrent neural networks are used a lot in price prediction, or something we call as time series data. Now, it is also possible to use different combination of neural networks together. You can always use CNN plus RNN. In fact, that is also very commonly done in a lot of problems because CNN is better at remembering things compared to recurrent neural networks. So you train everything with CNN, and using that training, you use RNN to get your output. All right. So this is different types of neural network. Then you have perceptron. The perceptron algorithm refers to a binary classification ML algorithm. So where have you ever have two classes? For example, you can have yes or no, or you can have true or false, or any such classes. You can have what we call as the perceptron algorithm. Okay. So the building blocks are neurons, weights, and activation functions. All right. So we already know what neurons are. We'll cover weights and activation function. So it has a single node or a single neuron that takes data as an input and predicts a class label. So what happens? You have one neuron. Information is being fed into this neuron and it is making some prediction. All right. So let's say, for example, you have, what would you say? You have money laundering, right? Now we are trying to classify whether a person is involved in money laundering or no. We have yes and no. Okay, we have yes and no. So what we do is we pass this information to a neuron. This neuron will give us some prediction. What it will do is it will give us probability of yes. Let's say, for example, 0.60, probability of no, 0.40. So it will label this specific observation as yes. Okay, it will classify it as yes. All right. So this is what we do. in neural networks. So these activation functions are weights times input plus bias. So we'll have some weighted inputs. We'll assign some weights to our inputs. Okay. And the bias is coming from the weight from the inputs itself. There will be some sort of bias for that input. So that is what we call as activation function. So we predict 1 if activation function is greater than 0. We predict 0 if activation function is less than or equal to 0. So inputs are multiplied by model coefficients. We find coefficients. For example, yesterday we were looking at y equals to beta naught plus beta 1 times x1 plus beta 2 times x2. These are coefficients. So our models are our weights are multiplied by these coefficients. So we try to use normalization or standardization techniques to ensure that we are not dealing with data that is too huge. The numbers that are too huge. We try to keep a limit to what is the value of these numbers that we are dealing with. So what we do is we just try to standardize or normalize. All right. So this is perceptron algorithm. In perceptron algorithm, you have to remember you have one neuron, only a single neuron doing all the decision making for you. All right. So we first initialize random weights. We randomly assign some weights. That weights are assigned by the algorithm. All right. Then we set a threshold y. We set this threshold. We keep repeating, we keep changing the weights until it is less than this threshold, or you have specified some maximum iterations. Maximum iterations refers to how many repeated runs you want. So what we do is we specify some value. Let's say we say 20. That means our weights would be run 20 times. If in that 20 times we are getting lower than a threshold, that is fine. Otherwise, once you reach the maximum number of iterations, it will take the lowest, it will take the best possible value, and it will stop right there. So now we are trying to update the weights here. Okay, we are trying to update the weights here. So this is the formula for calculating the next weight. Okay, so you have W, it's a vector. Remember, always it's a vector. So here you will have the previous weights. Here you will have learning rates. Learning rate refers to how quickly your model is adopting to the algorithm, to the problem. And this ranges between 0 and 1. Okay. All right. So by default, we take the learning rate usually as 0.1 or 0.01. So these are considered good values. So we start off with that. So you take the previous weight, you add the learning rate, and you calculate the error. You calculate the error between the predicted value minus the actual value times x times what is our input. And this is how you calculate the weights. So here we have these 4 points. So we are trying to calculate the initial weights. The initial weights at 0, 1 are weights 0, and the learning rate is 1 by 3. So this is how you calculate weights. Since this is a two-plane problem, you calculate for x and for y. You try to calculate the value for both x and y. So for x, you have 0 plus the learning rate times the error. The error rate is -1 times the x value. All right, so you have this x value. So this error rate is from this line. It is from this line. So the answer is 1 by 3. Similarly, for y, you take 0. For y, it is 1. 1 plus 1 by 3 times the error is again -1 times, sorry, the error is -1 and the x value is 0.5. So the answer is 5 by 6. So this is how you calculate the next weights. So weights at 1 would be 1 by 3 times 5 by 6. Similarly, you can continue on for this step. So you can carry on moving forward on how you want to calculate these weights. Okay. So this is the next stage. So here we are again trying to calculate the next level of weights. Okay, so this is our first correction. Now previous line was something like this. So now we are getting closer to these points. All right, so we calculate it again. We take the starting point plus the learning rate times the error and the x value. So you get 2 by 3 and then you also get 2 by 3. So now this is what our line looks like. The previous line looked like something like this. The initial line looks something like this. Okay, so here we are just rotating and then we have separated the blue points from the red points. So that is how you keep correcting your weights until the point you find your ideal weights based on your use case. Whatever use case you're working with, you're trying to find that ideal value of weight. All right. So this is what a neuron looks like from inside. So this is our computer neuron. So we are getting some input x1, we are giving it some weights. All right, all the way. So here we have some integration function that is going to aggregate all these inputs into something sensible, into something that is understandable. And this formula is written over here. Weight I times x of I plus constant p. So you're taking the summation over the number of neurons you have. And then you have an activation function. These activation functions decide if you want to activate the neuron or not. All right, these functions decide if you want to activate the neurons or not. It's similar to our human body. For example, we see something, we have a reaction to it. What if you see something and you're not able to react to it? You don't have the sufficient time, or you decide that you don't care about it. Reaction, I'm talking about facial reactions here. I'm not talking about, the reactions that are happening in your head. I'm talking about facial reactions. Now, if these reactions are not happening, that means those specific neurons were not activated. Similarly, here, these neurons are controlled by their activation function. So you define the activation function, and we have the output. This is a binary step output. This is a binary step, activation function. All right. So we'll cover these activation functions in a little bit. So moving forward, multi-layer perceptron refers to multiple neurons working in collaboration to come to a decision. So in multi-layer perceptron, you have the input layer that will take all the inputs. You have the output layer. The output will give the answer. And you have the the hidden layer. This hidden layer is where all the processing happens. So they are called hidden layers. Okay. So the input receives some functions. So it has received 4 different types of input. Now you have input 1, 2, 3, 4. You have hidden layer 1, 2, 3, 4, 5. Hidden layer 2 is 1, 2, 3, 4, 5, 6, 7. And then you have 3 possible outputs. Now what will happen is this input 1, it will be sent to all these hidden layers. So you will get these combinations 1, 1, 1, 2, 1, 3, 1, 4, 1, 5. The decisions would be processed. So for it 1, 1, you will have 5. Sorry, you will have 4 values. Here you will have 4, 4, 4, and 4. And these all values would be assigned by their weights and their bias. Afterwards, from 1, 1, you will send it to 7 different neurons. So from this hidden layer, you will get again 1, 1, 1, 2, all the way to 1, 7. You get 2, 1, 2, 2, all the way to 2, 7. So again, all the decisions are being made at different node, and then they are sent to these output layers. This output layer will select the best output, and that will be sent forward. Okay. So these hidden layers are the processing machines. These hidden layers where all the magic of neural networks is happening. Everything you do, it's happening here. All right. So they become very important. So let's move forward. So now you have these activation functions. You have a whole different set of activation functions that you can use. Okay. So you have the identity function. You have this step function. We have seen ramp function that looks like a ramp, and sigmoid function. So here, how does it work? This activation function goes to 1 if f is greater than 0. Otherwise, it stays at 0. And here you have a ramp. If f is greater than 1, it will go up by 1. If it is between 0 and 1, it will go up by the value of f. And if it is 0, f is less than 0, it will stay at 0. And sigmoid functions are calculated using 1 plus e of f. This is our identity. This is our eigenvalue. All right. So you have different types of different types of neural networks. So you have sigmoid function. These are usually used in binary classification. All right. These range between 0 and 1, and they are used mostly in binary classification. Tan H So this is used to bring the mean closer to 0. This will help the next function do better calculations. So that is the purpose of tan h. Okay. Then you have Relu. Relu stands for rectified linear unit. Okay. This is the most commonly used function, and it is less expensive. Less expensive how? Computationally than sigmoid and tan h, because the calculations, if you notice this equation, the calculations are a lot simpler. Okay. Then you have softmax function. Softmax is used for binary classification. You have leaky Relu. That is a variation of Relu function. So these are the different kinds of activation functions that you can use. All right. So why we use non-linear functions like this, and even this max out? We use it because without these activation functions, it is then just becoming a linear regression problem. All right. Then it is just becomes a linear regression problem. And this is done to introduce some sort of non-linearity into the output of a neuron. Okay. So that is why we use this function. All right. So let's move forward. So this is a error. So this is a 3D plane. You're visualizing a 3D plane here that is displaying some sort of error. Okay. So error is very useful. So an ideal error will have one minimum value, and you want that value to be 0. Okay. So here you have this plane. You want this value to have only one minimum value. Here you might notice you have multiple minimum values. So these values are going to cause some issues. Okay. So we try to have a maximum of one, what do you call it? Error surface. Okay. And so here we can also get the direction and the magnitude. All right. So we are trying to visualize the error. We are trying to see how we are getting the error and where we are getting the error with what strength. So we use the gradient descent. We use the gradient descent to find the local maxima and minima of any function. And this is done to minimize the cost and loss function. So minima is the minimum value. This is where the function is at its lowest value. All right. And maxima is when the function is at its highest value. So we use gradient descent to figure out the minima and the maxima. And using this minima and using this maxima, we can figure out what sort of error we are getting. Okay. So we try to minimize this error. All right. So moving forward. So neural networks are part of deep learning. Deep learning refers to, it's called deep learning because you're focusing on much more complex problems, which come under the comprehensive term AI. This is part of artificial intelligence. And ANN is used as a part of neural networks. Okay. So we define some activation function, and based off of that, our model is running. Convolutional neural networks are primarily used in image processing and are used to process pixel data. So whenever you're dealing with any sort of image video processing related problems, we use convolutional neural networks. Okay. RNN is where the previous step is used as the input for the current step. So you have some input coming in, you get a step. That step forms the input for next layer. All right. So this is used for sequence classification, that is sentiment and video classification, sequence labeling, your speech tagging, and name entity recognition. So basically, you're trying to identify sequences here. All right. You're trying to understand what sort of sequence you're using. These are also used for price predictions a lot of time. You'll see something called LSTM. You'll come across this. This is part of RNN. All right, long short-term memory. Okay. So moving forward, in artificial neural networks, you have input layer, you have the hidden layer, and you have the output layer. In input layer, it can take several different formats. Hidden layer is where all the calculation is done. Output layer is where you're getting all the output. Okay. And then the association between, one second, guys. The association between neurons and input neurons and output neurons can be directed as edges of with the weights. Okay, each input is given some weight. We have seen that we calculate the weight, any random value at first, and then we try to get it as close to the ideal weight as possible. Okay, and these weights represent the strength of neurons inside the artificial neural network. If weighted sum is 0, then we add bias to make sure that we are getting a non-zero output. Okay, that means we are not trying to have a null response. Bias has the same input and weight equals to 1. The total of weighted inputs can range from 0 to infinity. They cannot fall below 0. If your weights are some for whatever reason going below 0, in that context, you have made some mistake. All right. So this is the theoretical part of neural networks. Now let's switch over to the coding part. So just give me a minute and I'll share the code and we'll start working on our code. All right, so let's take a look at the code. And here we are again working with money laundering related issues. All right, we are trying to predict if a person was involved in money laundering or not. So we are again doing binary classification. So we are trying to do some sort of binary classification. All right. So we'll import the necessary libraries and we'll import a data set. So let me just quickly restart the kernel and then we can begin. All right. So we'll import the necessary libraries. We'll read our data. And this is what our data set looks like. So we are taking a look at the total amount. We are taking a look at how many transactions are done during the weekend, the night, how many transactions a person is doing to different customers over a 1 week period, over a 7-week period, 7-day period, and over a 30-day period. All right. And then you're checking the average amount over a 1-day period, 7-day period, and 30-day period. And then we are checking how many different terminals they are transferring this money to. So this terminal refers to how many different banks they are transferring the money to. Then the risk factor associated with it, and then whether the person is involved in fraud or not. 0 means no, 1 means yes. All right. So then we check for information. We ensure we don't have any null values. All right. And we can see that we have all numeric data. So we don't have to be involved in any sort of encoding. Without encoding, we can just carry on doing our work. All right. Then we'll quickly just take a look at the describe. We notice that we don't have huge values that we are dealing with. Obviously, most of them are some sort of smaller amounts. So these are amounts in the thousands. Okay, don't think that we are just looking at 80, whatever currency you want to use, rupees or dollars or euros. We are looking at 8,000. All right, here we are looking at 61,000, 10,000, 13,000. All right, we are looking at 900. We are looking at 31,000, like that. Okay, then we'll take a look at the correlation heat map. So based off of this correlation heat map, it is very difficult to read. What we can do instead is we'll draw a correlation matrix. So this is our correlation matrix. Again, because we have 16 columns, it is difficult to read. But for text amount, this is the correlation. For text during the weekend, this is the correlation. All right. So here, just try something. Just trying something. I'm not sure if this will work or not, but let's try anyhow. There we go. So now this becomes a lot clearer. We should probably increase the size a little more. So let's make it 2020. So there we go. So now we can see the correlation. We can observe that there are some values that are highly correlated to each other, but most of them are showing little to no correlation. All right. And it is even going all the way into the negatives. Okay. So then we can take a look at the pair plot. This pair plot will give us the scatter diagram for all these values as well as the histogram. So let's just wait a minute for the pair plot to be ready. Since we are dealing with a large data set with 16 columns, it will take a little bit of time. We'll remove this correlation matrix because it is not giving us the information we need. So yeah, this is taking slightly longer than I expected. Here we go. So using this, we can identify patterns. We can identify patterns in our data. As such, we can see that we are not facing any issues of high degree of correlation with each other, right? I think the highest was a 30-day window in relation to 7-day window for customer ID. All right. And aside from that, we had customer ID over 30-day window by customer ID over 7-day window. Again, we don't have high degree of correlation, so we don't have to worry about it. Then we'll quickly just check the data types to ensure we didn't miss anything. We'll get the column names. So these are all the columns we have. Then we'll define the min-max function. So here what we are doing is we are trying to reduce the range of our values to be between 0 and 1. All right. So we'll do that. We'll run this function. We don't need to run these lines. So I'll just quickly remove them. And then we'll what do you call it? We'll take our X values. We'll take what we are doing here is we are using location. So we are saying when you use this, this refers to rows, how many rows you want to take, and this refers to columns. So we are doing it using index slicing. So here we are saying take all the rows, and for column we are saying start from index position 0 and go to 50. Now in Python, this value is not taken. So that means basically what we are saying is start from column 0, 1, 2, all the way until column number 14. That is these columns we are taking. So we are taking 15 out of the 16 columns. So we'll quickly take these columns. And we have these arrays now. And similarly, we'll take our Y value. So we have zeros and ones. Okay. And then standard procedure, we come back to standard procedure. So we'll take our sklearn for train test split, and we'll just quickly verify the shape. So here we have the shape for our X variables and our Y variables. So for this, we are using Tensorflow and Keras. Now Tensorflow is a framework that allows you to use deep learning algorithm within your library. Whatever you're working with, you can always use Keras for it. Okay. So you have Tensorflow. Similarly, you have Keras. Keras is where all the models are built. Okay. So this provides the interface for neural networks. Okay. So up until 2.3, it supported various multiple backends like TensorFlow, Piano, PlateML, but now it is basically integrated within TensorFlow itself. All right, so TensorFlow itself includes the latest versions of TensorFlow includes these Keras frameworks as well. All right. So here we'll import TensorFlow, we'll import Keras. From Keras, we'll import sequential. Sequential will define a model. our model will be built in a sequential manner. These dense will form our layers. All right. So batch normalization is done to normalize any batch, and then you have some backend support for things like metrics that you might want to use. So we'll just quickly import these libraries. So then we are building a model. So here we have initiated a sequential model. So we are building our input layer. Here we have to specify the input dimension, and this input dimension should match the number of columns you have. That is very important. Okay. So that is very important. We have to remember that. All right. And then we are building our layers, and then we are building our final layer. And here we are using linear as our activation function. But since this is a binary classification, let's try with sigmoid. Let's see if it makes any difference. All right. So then we compile the model using an optimizer, the loss function. The loss function we are taking is called as mean squared error, and the metrics we are measuring for is accuracy. So ADAM is an optimization technique that we use for gradient descent. So we are trying to find, okay, so we are trying to reduce our error. So we use this optimization function, and this function is called as ADAM. Okay, so what it will do is it will inherit the positive attributes of previously used methods, and it will work on it. Okay. So it gives much higher performance than you had previous measures like RMS prop, ADA grad. So it will take these optimizers, and it will combine their features and form this optimizer. So let's compile our model and let's take a look at how it works. So it is compiled. Then we try to train the model on a data set. So we will take the training data set and we'll train our model. Here we are specifying the epochs. Epochs are number of iterations you want your model to train for. And batch size is 32. Batch size means how many inputs you are sending to your neurons, sending to your network. Okay, so if you are having batch size as 32, that means you're sending 32 inputs at a time. So let's run this and see how it works. We have also added validation split, and we are using validation split to ensure that our model can be used in different data sets. So it has started running. So here we can see, observe 4 variables. So our variables are loss, accuracy, validation loss, and validation accuracy. So let it run. It will take a few minutes, a couple of minutes to run, and then we'll quickly go through all these parameters. Okay, then we'll quickly evaluate our model. So what we are trying to do with this is we are trying to achieve the highest possible accuracy. As you can see that we have probably already achieved the highest possible number of accurate outputs you can get with these epochs. So normally what you should do is, once you run with the higher number of epochs, because we don't know what the ideal number is. So here it is more of a trial and error thing. So what you do is you run for different values of epochs, and then you observe where you are getting good percentage, where you are getting the highest accuracy and the lowest error. All right. So wherever you're getting the highest accuracy and wherever you're getting the lowest error, that should be your stopping point. Now here we can observe that our accuracy and validation accuracy hasn't improved over time. So that means we probably don't have to run it for 20 epochs. That would just be a waste of time in this scenario. So 20 epochs means 6 seconds. It is taking around 2 minutes to run. So you can probably save a minute or a minute and a half by optimizing this. All right. You can also play around with the batch size to try. So here we have the total number of parameters that were available to us and how many of them were trainable and how many of them were non-trainable. So the trainable attributes were 3,901,000. So let's evaluate. So we'll run it on a test data set. So we run it on a test data set and we get an accuracy of 99.18%. And we evaluate again on a training data set just to check, and we get 99.1, which is the same here that we were getting. So then we predict. And then we take the R2 score. The R2 score is not very high. That means despite good training score, maybe we can make some improvements in our model. All right. Can also, try different accuracy measures to see how we can work it. All right. And then we'll quickly visualize. You can see that the accuracy barely changed. So that means we shouldn't have run for that many epochs. And maybe we shouldn't have changed the activation function from linear to segment. All right. So you can try with different activation functions as well and see how they are performing. And this is the loss. As you can see, the loss also didn't change a lot. All right. So this is artificial neural network and this is how it works. So I just want to say thank you everyone who was tuned in and watched this domain analytics session over the last few days. So I hope this helped you learn how we can apply machine learning algorithm in financial securities. All right. So thank you everyone for joining and I hope you have a good day.